Hello everyone. Today in this video let us discuss all these 5 questions solutions from exercise 1.1 chapter 1 real numbers of 10th grade NCERT book. Okay, let's start. Yeah, let us start exercise 1.1 from chapter 1 real numbers grade 10 NCERT book. In this exercise you have one first question. Use Euclid's division algorithm to find the HCF of 135 and 225. Let us do this first question first. So, according to Euclid's division algorithm, we have that A is equal to BQ plus R. A is equal to BQ plus R, where Q and R are quotient and remainder when A and B are divided. Here A is 225. Let us think A is 225 and B is 135. Yes, A should be greater than B to divide. So, let us divide 225 with 135. 135 ones are 135, 90. So 90 is the remainder. 1 is the quotient and 90 is the remainder. So according to Euclid's division algorithm, we can write the first step as 225 is equal to 135 times 1 plus remainder 90. Okay, so as the remainder is not 0, we have to continue the division process the same. Now applying division algorithm on 90 and 135, let us divide these two. 90 times 1 gives you 90. Let us subtract again. You will get 45. So again the remainder is not 0. So let us write according to division algorithm 135 is equal to 90 times 1 plus remainder 45. Next, as the remainder is not 0, let us continue the division again. Let us take the remainder as divisor now and the previous divisor as dividend and divide these two by applying division algorithm for these two numbers continuously. 45 twos is 90 exactly. So we got 0 remainder. So our third step is applying division algorithm for the third division. 90 is equal to 45 times 2 plus 90. Sorry, plus 0 remainder. We got 0 as the remainder. Now at this stage where you got 0 as a remainder, the divisor at that stage is HCF. This is called HCF. So the HCF of 45 and 90 is also 45. And HCF of 90 and 135 is also 45. HCF of 135 and 225 is also 45. So we can write as HCF is equal to HCF of, let us come from the beginning, 135 and 225 is same as HCF of 90 and 135 is also same as HCF of, at every stage whatever numbers we have taken, those are all having the same HCF is equal to, for all these HCF is 45 only. Is equal to 45. So now let us do the second question. Now let us do the third question. 867 and 255. Find HCF of 867 and 255 using Euclid's division algorithm. So let us first divide these two numbers with one another. 255, 867. So 255 threes are 765. Subtract. You will get here 2, 0, 1. 102 is the remainder. So the first step of using a division algorithm is 867 is equal to 255 times 3 plus remainder 102. Okay, next let us divide this continuously. 102 with 255. Applying division algorithm on 255 and 102, we will get still 102 twos are 204. So let us subtract. You will get here 51. So let us write the second step of the division algorithm, that 255 is equal to 102 times 2 plus the remainder 51. Now as the remainder is not 0, let's continue the division still. 51 is divisor and 102 is our dividend now. Applying division algorithm on these two numbers now, we will get 51 times 2 is 102 exactly. So we get 0 remainder at this stage. So let us write the third step. 102 is equal to 51 times 2 plus 0 is the remainder. Okay. Now at this stage where you got 0 as a remainder, this is our HCF. The divisor at that stage is HCF. HCF. Okay. Therefore, HCF of our numbers 867, 255 is same as HCF of the next pair 102 and 255 is also same as HCF of the another pair 51 and 102. So for all this HCF is the same number 51. Let's go to question number 2. Now let us do the third question. 867 and 255. Find HCF of 867 and 255 using Euclid's division algorithm. So let us first divide these two numbers with one another. 255, 867. So 255 threes are 765. Subtract. You will get here 2, 0, 1. 102 is the remainder. So the first step of using a division algorithm is 867 is equal to 255 times 3 plus remainder 102. Okay. Next, let us divide this continuously. 102 with 255. Applying division algorithm on 255 and 102, we will get still 102 2s are 204. So let us subtract. You will get here 1, 5, 51. So let us write the second step of the division algorithm, that 255 is equal to 102 times 2 plus the remainder 51. Now as the remainder is not 0, let's continue the division still. 51 is divisor and 102 is our dividend now. Applying division algorithm on these two numbers now, we will get 51 times 2 is 102 exactly. So we get 0 remainder at this stage. So let us write the third step. 102 is equal to 51 times 2 plus 0 is the remainder. Okay. Now at this stage where you got 0 as a remainder, this is our HCF. The divisor at that stage is HCF. HCF. Okay. Therefore, HCF of our numbers 867, 255 is same as HCF of the next pair 102 and 255 is also same as HCF of the another pair 51 and 102. So for all this HCF is the same number 51. Let's go to question number 2. Now let us see the second question. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Okay, you need to prove that these are odd positive integers using Euclid's division algorithm. So using Euclid's division algorithm, we have that a is equal to bq plus r. This is our Euclid's division algorithm. So according to this, r should lie between greater than or equal to 0 and should be less than b according to division algorithm. So let us think now, let a be any positive odd integer. Let us take a be any positive odd integer. And let us think b as 6. Let us think b is equal to 6 according to here. Whatever q before whatever number is there, that number you take it as b is equal to 6. Now, according to Euclid's algorithm, we can write a is equal to bq. b means 6. 6q plus r. Where here r should be lying between greater than or equal to 0 but less than, b means 6. It should be less than 6. So r can take values. R is equal to starts from 0 1, 2, 3, 4 and 5, not 6, up to 5, 0 to 5, all the numbers. So what happens? Let us see in each case if r is equal to 0. If r is equal to 0, let us substitute r is equal to 0 in this. So you will have 6 cube plus 0, which is a is equal to 6 cube plus 0, which is 6 cube, which is equal to 6 cube. And similarly, if r is equal to 1, what happens if r is equal to 1? A is equal to 6 cube plus 1. Just substitute in this r value. And next, if r is equal to 2, a is equal to 6 cube plus 2. Similarly, let us write. If r is equal to 3, a is equal to 6 cube plus 3 and so on. Let us continue. If r is equal to 4, a is equal to 6 cube plus 4. If r is equal to 5, a is equal to 6 cube plus 5. Now, if you observe carefully all this, if a is equal to 6 cube, this is a definitely even number because it is divisible by 2. Exactly, it is divisible by 2. So, we can call it as even number. Similarly, 6 cube plus 2 is also an even number because it is also divisible by 2. 6 is divisible by 2 and 2 is also divisible by 2. So, the whole number it is divisible by 2. So, it is an even number. Similarly, come to here. A is equal to 6 cube plus 4. This is also for the same reason. This is also an even number. So, you have to understand that all the numbers that can be either odd or even. So, either odd or even means these are already even numbers. These are all even numbers. So, if these three are even numbers, the remaining other three numbers which you feel here, a is equal to 6 cube plus 1, you can also understand if 1 is added to even number, this becomes as odd number. And similarly, if 6 cube plus 2 is even number, if you add 1 to that, you will get 6 cube plus 3, which gives you odd number again. Similarly, if 6 cube plus 4 is even, if you add 1 to that, you will get 6 cube plus 5, which is also odd. So, all the numbers either even or odd. So, whatever even numbers are there, the remaining other numbers are odd. So, the alternate numbers are all odd. So, you proved now a is equal to 6 cube plus 1, a is equal to 6 cube plus 3 and a is equal to 6 cube plus 5. These three numbers are all odd number representations. So, you can say that every positive odd integer which is in the form of 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5, these are all odd numbers. So, hence proved. Let us go to the question number 3 now. Now, let us see the question number 3. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So, in this type of questions, wherever you observe the number, like the word maximum number, that means it is the obtained by calculating the HCF. So, always remember that wherever maximum is asked, you need to find the HCF. So, this can be calculated easily by finding HCF of these two numbers 616 and 32. So, let us write HCF of 616 and 32 using Euclid's division algorithm. So, let us divide these two numbers first. 616 is divided with 32. So, first 32 ones are 32. As 32 2s is 64, more than that we can take 1s are. So, if you subtract 9 and here 2 and bring 6 here, 296. So, 32 table 9s are 288. So, after subtracting you will get 8 here. So, as the remainder is not 8, we need to continue the division with this 8. So, in this first step, we can write the division algorithm as 616 is equal to 32 times 19 plus 8. So, let's continue the division with this 8. Take this 32 as the dividend. So, 8 4s are 32. Exactly, we get a 32 and 0 remainder here. So, where you got 0 remainder at this stage, this is our HCF. So, we can write the second step as 32 is equal to 8 times 4 plus 0. And next, we will write, therefore, HCF is this number, 8, the divisor at the last step. So, this is our HCF. So, HCF of 616 and 32 is 8. That means the maximum number of columns which an army contingent of 616 members whichever to march behind the army of 32 members in the parade is 8. So the total number of columns which the march is 8. So let us go to the question number 4. Now let us come to question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So remember carefully, square of any positive integer should be of the form either 3m or 3m plus 1. You have to prove using Euclid's division lemma. Okay. According to Euclid's division lemma, we have A is equal to BQ plus R. Right? A is equal to BQ plus R, where R should be greater than or equal to 0 but less than B. This is the condition for R, remember always. Let A be any positive integer. Let us take A be any positive integer and let us think B is equal to 3. Why B is equal to 3? B comes from here. B, let us think whatever number is here, let us take it as B. Now, according to division lemma, we can write A is equal to B means 3 here. So, 3Q plus R, where R should be greater than or equal to 0 but less than, here B, less than B means less than 3. So, R can take the values, R is equal to either 0 or 1 or 2 only, not 3. So, it can have 0 also because less than or equal to, greater than or equal to 0. So, 0, 1, 2. This may be the R values. So, if R is equal to 0, what happens? If R is equal to 0, put R is equal to 0 in this. So, A is equal to 3Q. Right? A is equal to 3Q. Here, we want actually square of any positive integer. So, let us make square of this A. So, A square becomes 3Q whole square. 3Q whole square, which is nothing but 9Q square. This 9Q square can be written as 3 times 3Q square. 3 times 3Q square. So, 3 into 3 is 9. So, I just split it like 9 is equal to 3 into 3Q square. So, what do you understand by this? 3 into some integer this is. So, 3 into some integer m. You think it as m. So, assume m is equal to 3Q square. Some integer. This is some integer. So, a square is equal to 3m. So, you got a square of positive integer is of the form 3m. 3 into m is 3m. Now, coming to if r is equal to 1, what happens? If r is equal to 1, a is equal to 3q plus 1, right? So, let us take a square now because we want square of any positive integer. So, a square will be 3q plus 1 whole square, which you can write it as like in the form of a plus b whole square shape, which is 3q whole square, which is 9q square plus 2ab, 2 into 3q into, so 2 into 3q means a, that is, into b is 1 plus 1 square. So, this is actually a plus b whole square form. So, 9q square plus 6q plus 1 is the a square. So, this you can write it as, I will take out 3 common in this, like 3 if you take out 3q square plus 2q and plus 1. So, if you observe this, you assume as m. So, you can write it as 3m plus 1. Now, you have that a square is of the form 3m plus 1, where m is the 3q square plus 2q. You assume that this has m now. M or any positive, any integer. So, 3m plus 1. Now, similarly, you can get also if r is equal to 2. What happens if r is equal to 2? Similarly, a is equal to 3q plus 2. Therefore, a square will be 3q plus 2 whole square, which you can again expand according to form of a plus b whole square shape. A square is equal to 3q whole square, which is 9q square. 2ab shape in the middle, 2ab means you will get 12q plus 2 square means you will get 4. This 4 I will split as 3 plus 1. So, I can write 9q square plus 12q. This 4 I will write it as 3 plus 1. No effect. So, you can write like 4 as 3 plus 1. So, next what I will do is in the first 3 terms I will take 3 common. So, a square is equal to 3 into 3q square plus 4q plus 3 is there. 1 again plus 1. So here also you got a square is equal to 3 into, this is all you think as some integer m. So 3m plus 1 again. So 3m plus 1. Here the integer is m you think as 3q square plus 4q plus 1. So here also you got a square is equal to 3m plus 1. Here also you got a square is equal to 3m plus 1, or sometimes a square is equal to 3m also. So we proved that square of any positive integer is of the form either 3m or 3m plus 1 or 3m plus 1 again. So either 3m or 3m plus 1, a square is equal to. So okay, let us go to question number 5 now. Now let us see question number 5. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Understand clearly? You need to show that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Okay. So using Euclid's division lemma. So according to Euclid's division lemma, we know that A is equal to BQ plus R, where R is greater than or equal to 0 but less than B. So here let us think A be any positive integer. Let A be any positive integer and B is equal to, let us think B is equal to 3. Let us think B is equal to 3. Now here A is equal to 3q plus R. Substituting B as 3. Now here 0 lies, R lies between 0 and 3. So R can take the values 0, 1, 2. Only these three values. So let us think if R is equal to 0. If R is equal to 0, A will be equal to 3q. So as we want cube of any positive integer, so let us cube it on both sides. A cube will be equal to 3q whole cube. Okay, right? 3q whole cube means you can write as 3q into 3q into 3q, which is 3 3s are 9 3s are 27 q cube, which you can also write it as 9 into some number, which is 9 3s 27 q cube. So 9 into 3q cube. What do you mean by this? Let us think this as some integer. Like assume this as m. So you will get it as 9m. So a cube is equal to 9m we got. So that means cube of a number is a form of 9m. Now let us take if r is equal to 1. If r is equal to 1. So if r is equal to 1, a is equal to 3q plus 1. And cubing on both sides again, a cube will be equal to 3q plus 1 whole cube. So you know what is the formula for a plus b whole cube? A plus b whole cube is equal to, I'll write here, a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. So let us substitute the values of a and b in this and write down this as 3q whole cube. So which is equal to 27q cube plus 3a square b, 3 into 3q into b. So which gives you 27q square plus 3ab square, 3 into 3q into b square 1 square. So which is nothing but just 9q plus 1. 1 cube is 1. That's why 1. So finally here what we will do is let us take 9 common in up to these three terms. So if I take 9 common, I'll take 3q cube inside plus 9 3s again 27 plus 9 1s 9, 1q or just a cube, which is 1. So what did you understand here? A cube is equal to 9 into something plus 1. So this something you can assume as again m. So we can write a cube as 9m plus 1 again. So now coming to if r is equal to 2. If r is equal to 2. So you will get a is equal to 3q plus 2. So write a cube is equal to, cubing on both sides, 3q plus 2 whole cube, which is equal to, apply the formula like this again, a cube plus 3a square b plus 3ab square plus 3 plus b cube. So we can write it as now a cube. So 3q whole cube. So which is 27q cube again plus 54q square. 3a square b I am multiplying plus 3ab square. 3 into 3q into 2. So I'll get 36q plus 2 cube. 2 cube is 8. So in this all these three terms, or in all the four terms, I'll take first three terms again 9 common. If I take this 8, it's okay. Write 9 common. 3q cube plus 9 6 are 54. So 6q square plus 9 4s are 36. So 4q plus 8 as it is. So now I get this all part as something you think as m. So 9m plus 8. So we can write it as 9m plus 8, where m is the 3q plus 6q square plus 4q. So we understand that here a cube is 9m, here a cube is 9m plus 1, here a cube is 9m plus 8. So what do you understand? Cube of any positive integer can be written in the form of 9m or 9m plus 1 or 9m plus 8. Okay, so we'll meet in the next video. Bye.